Hi, this is Professor Fernandez. This is class note C in lesson 3. Let's consider this sold IVP here, this initial value problem, second order linear ODE. Here it is, and here are the initial conditions. And the first thing we want to do here is prove that this initial value problem has a unique solution on this interval. So that is a giveaway to going back to the existence uniqueness theorem. So I'm just going to scroll up here and remind you, we talked about this in the previous class notes. Here are my scribbles from that last video, so I will erase them so we can use all of this to apply it to the new example we're doing. But remember, long story short, we are talking here about a homogeneous soled with initial conditions given, and for this theorem to work, we need P of t and Q of t to be continuous on the interval that contains the t value of the initial conditions. So those are all of the requirements. So what I'm going to do now is scroll back down to where we were, and we're going to start applying this theorem. First thing I have to do is I have to put the ODE in standard form. This ODE is not in standard form. So to do that, I'm basically going to divide by t squared. So I get y double prime, so I'm working on 1 here, plus 5 over t y prime minus 5 over t squared y equals 0. And from there, I can identify the p of t function, there it is, and the q of t function, there it is. Now, these functions are not continuous at 0. So they're problematic there. They're continuous everywhere else. But that's okay, because we are asked to look at the interval that excludes 0, right? So 0 is not included in this interval. So these are both continuous on the interval that we are interested in. This is 0, 2. So great, and this is a homogeneous second order linear ODE. So all of the other requirements are satisfied. So we conclude that yes, the theorem applies. And I'm just going to scroll back here to make sure I have the reference for that theorem. Excuse me, it's 3.1.1. So we'll put that down here. So yes, theorem 311 applies. Great, so we have proven that there is a unique solution. And then the second part of this example asks you to find that unique solution. So to do that, we're going to use a different theorem. So I'm going to scroll up here a little bit closer and take a look at this theorem. So let's read what this theorem says. This theorem says, suppose P and Q are continuous on an interval. Same part of the supposition of the existence uniqueness theorem. Consider the homogeneous soled, so, same type of ODE that we're looking at. Now, additional conditions, suppose that two solutions, y1 and y2, of the homogeneous soled are known. The theorem says that the linear combination of these two solutions is again a solution. What is a linear combination? So if I just take those two solutions, y1 and y2, and I multiply them by whatever numbers you want, and then I add the result, that's a linear combination. So this theorem is telling us basically that if I know two solutions of a homogeneous soled, then I can take a linear combination of them, and it is again a solution. Great, so I'm going to apply that theorem now to this example, and let's figure out what is going to happen. So I'm going to scroll back down here, and looking here at what's given to us, we have two solutions, y1 equals t, and y2, I'm trying to change my color here, sorry, y1 equals t, and y2 equals t to the minus 5. Great, so what we're going to say here is then by theorem 3.1.2, the linear combination of these two solutions, t and t to the minus 5, is again a solution. Great, so basically I have a whole bunch of different solutions. If you choose C1 and C2 to be whatever numbers you want, this new function y of t is also a solution. So what am I going to do now? I am going to go up here and apply these initial conditions. Excuse me. Why am I doing that? I'm doing that because I know that there is a unique solution. So I have already found a function that is a linear combination of the two known solutions. And so you might think, oh my, there's a ton of solutions. There's t to the minus 5, there's this linear combination. But in fact, we know that there's a unique one. We just proved that. So to find that unique one, I'm going to start applying the initial conditions to this y function. So y of 1 is 0. So 0 equals y of 1. And I'm going to substitute in that y value here for t. So I just get c1 plus c2. And then the initial condition for y prime of 1 equals 1. So 1 equals y prime of 1. I'm going to go up here and just calculate the derivative, y prime of t. So what is that? So that's just c1 minus 5c2 t to the minus 6. And when I plug in 1 for t here, that little part goes away. So I get c1 minus 5 c2. And now I'm going to solve this system of equations. There are a variety of ways you can do that. I am going to subtract this second equation from the first. So I'm going to multiply this by -1 and then add. Another way of saying what I just said. And then what's going to happen there? So I get 0 minus 1, that's -1, equals c1 minus c1 is 0, c2 minus negative 5c2, that's c2 plus 5c2, that's 6c2. So that tells me that c2 is minus 1/6. And if I go back to this equation, c2 is negative c1, right? So c1 is negative c2. So I can plug in this minus 1/6, multiply by -1, and get c1 to be 1/6. So my conclusion is that y of t equals c1 times t plus c2, which is negative, so I'll put the negative in front here, plus c2 times t to the minus 5 solves the IVP. And this is how we are going to use part A now. This function solves the initial value problem that we started off with, this whole thing up here. I'm going to put it here in a big red box. Solves this initial value problem. We just proved that the initial value problem has a unique solution, meaning there is only one solution. So we, in part 2, have found a solution. Because of this uniqueness, we're done. We are guaranteed that this is the solution. There are no other solutions to this initial value problem. So that's the point of this example. I really wanted to show you how you would apply both of the theorems that we have learned thus far in the lesson to get you a unique solution to a second-order linear homogeneous ODE that satisfies the other conditions in these theorems. So that's how these two theorems work together to provide you with that.